Investigating intuitive usability between motion controls and standard gamepads in a virtual reality video game application. Presented for HCI Psych 522, Spring 2018 by Team Purple. Andrew Coe, Daniel Pierce, Edwin Martinez Velasquez, Stephen Campbell, and Joy Ziegler. Virtual reality is an emerging technology that is significantly altering the way we interact with digital environments. Advancements in mobile screen components, optics, processing power, and motion tracking have facilitated affordable consumer-grade VR headsets. Immersive interactive experiences such as video games are at the forefront of VR's current applications. In our research, we compared the usability of VR systems when using motion controls versus traditional non-motion controlled systems by having both gamers and non-gamers perform 3 tasks. These tasks measured their efficiency in terms of number of errors made, the lower the better, accuracy of the execution, the higher the better, and time of completion, the lower the better. We also utilized the standard system usability scale to determine the participants' perception of usability of each device. Our hypothesis was that a VR motion control interface is more intuitive to use than a gamepad. For the purpose of this experiment, we have defined intuitiveness as how usable, effective, and efficient a controller type is in a virtual reality game. Usability was measured using a system usability scale post-experiment. Effectiveness was measured through the number of errors and user input during the experiment, as well as accuracy for each game type. Efficiency was measured as the time, in seconds, taken to complete each task in the experiment. The focus of the work by Cooper et al. 2015 on the effect of sensory cues on task performance in a VR environment contributed to the belief we could prove our hypothesis. We found that motion controllers, which provide some pseudo-realistic multisensory cues, can provide better intuitive usability than the gamepad, which does not provide such sensory cues. For our sample, we recruited 32 participants from Iowa State by posting flyers on campus notice boards. The participants were equally male and female, and each gender group was further split into 2 equal groups, one having at least moderate experience with first-person shooter video games, and the other having no experience. The participants' experience level was self-reported, and we defined moderate experience as having owned a video game console gaming PC in the past or having played a first-person shooter video game within the last year. 2 independent variables were active in the experiment. The first was controller type, which consisted of a standard Xbox One gamepad and Oculus Touch motion controls. The second was video game experience level, which was split into gamer and non-gamer categories. Our 3 dependent variables, usability, effectiveness, and efficiency, were designed to constitute overall intuitiveness. Usability was measured using a standard system usability scale survey. Effectiveness was measured by weapon accuracy and number of errors during the completion of 3 tasks, and efficiency was measured as the time it took to complete the 3 tasks. We centered our experiment's design around breaking down the concept of interactive intuition into observable data. From that, we formed a methodology consisting of performance and usability. We further divided performance into effectiveness and efficiency. A physical health questionnaire was administered for pre-screening candidates for our experiment. The questionnaire contained questions on self-reported audio, visual, balance, and other general physical impairments. Only students with no reported physical impairments or ailments were selected as subjects of this study. The health questionnaire also included the health and safety warnings provided by Oculus Rift regarding dizziness, seizures, and blackouts. The Oculus Rift head-mounted display was used by each participant across all 4 groups and facilitated the virtual reality visual and auditory output for the users. Each participant played the same virtual reality game, which was designed in-house to allow support for both the standard gamepad control scheme as well as motion controls. The respective controls used were the Xbox One gamepad as the standard control input and the Oculus Touch controllers as the motion control input. All 32 participants completed the same 3 tasks, with 16 using the gamepad and 16 using the motion controls. We created 3 tasks for participants to complete as effectively and efficiently as possible. The first task was designed to be a basic dexterity test where the participants would fire a complete weapon magazine, reload the weapon, then fire the new magazine. The second task required the participants to eliminate 10 enemy AI that were placed around the game environment and were able to fire back. The third task was to get from the starting location point A to the objective location point B, all while taking fire from enemy AI. Upon getting killed, the participant would have to start the task from the beginning. For our procedure, each participant completed the experiment one at a time where we had them stand in an open play space. We reminded them that they could take their headset off and stop the experiment at any time for any reason. We gave instruction on their tasks and handed their randomly assigned controllers to them. The participants were then asked to put their headset on and were given 2 minutes to familiarize themselves with the video game's controls. However, we did not give further instruction. After 2 minutes were up, the application automatically began one of the randomly generated tasks. After completing the task, they repeated the measure with the other 2 tasks. Once the tasks were finished, the participant took the headset off. Shortly after, they were asked to fill out a 10-question SUS survey that gauged system usability of their controller type. An exploratory data analysis of the system usability survey showed usability of the motion control VR headset was ranked above average, resulting in an A score from the first-person shooter gamers and a B score from the non-first-person shooter gamers. Usability of the non-motion control VR headset by non-first-person shooter gamers was ranked below average with a percentile ranking equivalent to a D score. Based on our participants' perception of usability, it is clear that non-first-person shooter gamers found the motion controllers more intuitive to use. The summary statistics support our hypothesis and show that there is a discernible difference in terms of the usability of the VR controller scheme amongst the 4 groups as well as between each independent variable. Measuring usability resulted in no significant interaction but with 2 main effects. The main effect for groups tells us that gamers scored higher in the SUS than non-gamers regardless of controller type. Meanwhile, in the main effect for condition, players who use motion controllers regardless of gaming experience scored higher in the SUS than those who used the gamepad. Analysis using 2x2 ANOVA demonstrated that there was indeed a significant difference in the usability of the VR controller scheme between groups, first-person shooter gamer versus non-first-person shooter gamer, and between conditions, VR motion controls versus VR with non-motion controls. There were no interaction effects for the 2 independent variables, as indicated by the insignificant p-value of the F statistic. The results concurred with the exploratory analysis showing that usability is highest for the groups of first-person shooter gamers with VR motion control and lowest for both groups of non-first-person shooter gamers. In Task 1, the number of errors measured resulted in a significant interaction effect, indicating that the effect of controller type on number of errors was dependent on gaming experience. In analyzing the post-hoc Bonferroni, gamers outperformed non-gamers, but gamers were more effective with gamepads, while non-gamers were more effective with motion controller. Looking at player accuracy, we see a significant interaction effect indicating that the effect of controller type on accuracy was dependent on gaming experience. Once again, gamers outperformed non-gamers, and gamers were more effective with gamepads, while non-gamers were more effective with motion controllers. For efficiency in Task 1, there was a significant interaction effect. Like with the effectiveness measurement for Task 1, gamers had a smaller time of completion than non-gamers, but gamers were more efficient with gamepads, while non-gamers were more efficient with motion controllers. When analyzing the results for number of errors in Task 2, the data violates Levine's test, but since the sample sizes were equal, we carried on with the ANOVA results. Much like the number of errors in Task 1, we again see a significant interaction between the independent variables. Once again, gamers outperform non-gamers, with gamers being more efficient with gamepads, while non-gamers were more efficient with motion controllers. In the accuracy measurement for Task 2, Levine's test is also violated, but once again, there were equal sample sizes. We found that the effect of controller type on accuracy was dependent on gaming experience. In a post-hoc Bonferroni, we see the continuous trend that gamers outperformed accuracy, but they are more effective with gamepads, while non-gamers with motion controllers. Analyzing the efficiency and time of completion for Task 2 resulted in no significant interaction. Only the group variable, gamers versus non-gamers, resulted in a main effect of significance, meaning the gamers were more efficient than non-gamers. Number of errors in Task 3 resulted in no significant interaction, but once again a significant main effect with groups. This main effect tells us that gamers were more effective than non-gamers. While measuring number of errors for effectiveness in Task 3 didn't give us much information, accuracy did with a significant interaction effect. However, the trend continues in that gamers were more effective than non-gamers and that gamers were more effective with gamepads while non-gamers with motion controllers. The data for efficiency and time of completion for Task 3 violated Levine's test, but with equal sample sizes we proceeded. However, like Task 2, measurement of time, there was no significant interaction and only a main effect of groups on time of completion. The main effect showed that gamers were more efficient than non-gamers in time of completion. Our hypothesis that motion controls were more intuitive than a gamepad in a virtual game environment was supported by our research. We believe our results are significant because they imply that further refining these new virtual interaction methods could trigger exponential technological growth in multiple sectors, including social media, entertainment, business, medicine, and of course, games. If we parallel the concept to the advent of the smartphone, it is clear how important intuitive user interaction really is. Just as the iPhone exhibits the transformation of mobile technology through the simplicity and accuracy of touchscreen control, we believe virtual reality's motion tracking will drastically enhance the way we interact with digital environments. Precise hand gestures will eventually allow people to manipulate three-dimensional objects with the spatial acuity that is possible in real life. This will help us drive user experience innovation forward and eliminate many existing barriers between people and computers. We realized there are certain limitations to this experiment. The amount of gaming experience of the participants was self-reported, and the role it plays was not quantified. Also, the sample size of 32 participants was relatively small and within a limited age range with a mean age of 19.6 years. We found evidence that there was a difference in the intuitiveness of controller types. While not statistically significant in all the tasks performed, the data still shows that an inexperienced gamer with motion controls was more effective and efficient than an inexperienced gamer with a standard gamepad. In addition, the SUS results do show that motion controllers have higher usability than a gamepad. We believe these findings resulted from the concepts that body movement is a natural form of control and that motion controllers provide sensory cues which allow people to better interact with a virtual environment. This is in contrast to the multi-button input of a gamepad, which has high efficiency but lower usability. Observation of the participants as they took part in this study combined with the analysis of results suggests that additional research in the field is warranted to explore related research questions such as: how does task type affect the gamer's choice of controllers? How does game genre affect gamers' choice of controllers? And how does experience with a particular controller affect user satisfaction? There are several directions continued research on this topic could explore, like testing for base level understanding, performing age-based analysis, testing for different tasks, and more closely examining the performance aspect of various game controllers.